What was one of the other factors that affected reaction rates? Temperature, right? So we threw all that water on those pearl lizards. It was due to temperature, right? So temperature has an effect on the overall reaction rate. When we look at the rate law, though, do you see temperature at any point in time in this equation? No, right? So temperature isn't in here, right? But we know that it does have an effect on the overall rate of a reaction. So where does temperature come in, okay? So I've been kind of specific in talking about K, right? What is K again? Little guy, rate. This guy is the rate constant. And I've been very specific about saying, oh, it's a constant, right? But I've also specified one specific thing about it. It's a constant at what? A specific temperature, right? So it's only a constant as long as you hold the temperature of the reaction the exact same temperature. You start to modulate the temperature and the rate constant is going to change, okay? This is where the overall effect of temperature on the reaction rate comes into being, okay? It's via the rate constant, okay? Okay, so how does the temperature affect the rate constant? Or even go back further, how does the rate constant affect the rate? Right? What is the relationship between K and the rate of the reaction? Just going back to the rate law. Is it directly proportional or is it inversely proportional? Just going back to this guy, right? K and rate, how are they related to one another? They're directly proportional, right? The larger the rate constant, the faster the reaction rate, okay? So these guys, little rate constant and the rate of the reaction are directly proportional to one another, okay? So now we know that if we increase the temperature of the reaction, what's going to happen to the overall rate? It's going to increase, right? So there should be a direct proportionality as well between temperature and rate constant as well as the rate of the reaction, okay? Unfortunately, though, this proportionality is not linear. Instead, it is exponential, okay? So over here, we have a nice plot of how the rate constant varies as a function of temperature in Celsius, okay? So note that at the very beginning, it does appear to be linear. But when you scale out and you start getting to much higher temperatures, what happens? It takes this giant curve to the exponential, okay? And so the first dude to kind of study this and model the effect of temperature and how it plays a role in the overall rate constant was called this Arrhenius, right? Savant Arrhenius, okay? And he developed what is called the Arrhenius equation, which is essentially how we explain how temperature has an effect on the overall rate constant, okay? There are a lot of factors in this equation right here, but a few of them we already kind of know, right? What is little lowercase k? Already been talking about it. This guy is just the rate constant. Can we determine the rate constant of a reaction? Yes, right? What did we just do? Had a bunch of reactions. Once we had the orders and the rate law, we plugged it in, and what did we solve for? K, right? So yes, we can determine the rate constant of a reaction, okay? There's a couple other things in here that I'm not going to explain until a slide or a few down the road, but some things we already know. So for example, RT. What is R? Big capital R. This comes back from 151. We haven't really learned it in here. So R is the gas constant. And then what do you think T is? T is the temperature. And just to give you a little preview of what's going to happen, this little e to the a, this is what is called the activation energy, okay? So if we're going to be dealing with energies with respect to all of these various units, what value of the gas constant should we probably use? There's one value of the gas constant, one numerical value that depends explicitly on energy and not on atmospheres and liters and moles and kelvins. So the gas constant is going to take on the numerical value of 8.314, and note that the units are joules per mole times Kelvin, okay? So we explicitly have to use that gas constant whenever we use the Arrhenius equation, okay? Okay, so let's talk a little bit about this. What are these other various things that come into play? So we know what K is, it's a rate constant. We know what R and T are. So now we're going to talk about these other unknown little things that we're introducing, okay? The first one, this little A, is what is called the frequency factor. Okay, and we'll explain what the frequency factor has to do in a second. The second one here, this guy, this is called the exponential factor. Okay, it's everything e raised to. Okay, we also denote this as f, so f is equal to e to the minus. Why is it doing that? Minus, go away. Minus e to the a over rt. We will denote this as f, which is called the exponential factor. Okay, and I've already alluded to this fact. This guy is called the activation energy of the reaction. Okay. All right, so let's kind of model at least a little bit of portions of this exponential factor. Okay, so you guys remember back in 151 we talked about thermochemistry, right? And what was the big kind of story of thermochemistry? It was enthalpies, right? Enthalpies of reactions. Okay, and so if we had reactants that were at a higher energy state than products, what would be the overall sign of delta H for the reaction? So final is products minus initial. Oh no, my pencil is low. So final minus initial. If this guy is bigger than this guy, what's going to be the overall sign of delta H? Should be negative, right? So if delta H is negative, what do we call that? Exothermic or endothermic? Negative delta H. Okay, so an exothermic reaction. Okay, so in 151, we had our nice little reactants on this little energy diagram, right? And we were like, oh, and then they just fall to the products, right? That wasn't true, okay? So let's imagine this little reaction as an example of what actually has to happen when we undergo a chemical reaction, okay? So in this reaction, we're taking a molecule called methyl isonitrile, okay, and it is isomerizing to form acetonitrile. Don't need to know that, right? What happens with respect to this guy, though? We have this thing, and when it goes to product, how does it change? We had a carbon that was bound to the nitrogen. What has changed in the product? The carbon is now bound to what? This carbon is bound to a carbon, okay? So all that's happened is you had a molecule that was like this. In the reaction, this is broken and it's turned the other way, okay? It's isomerized, all right? So now to get from this, our reactant, to our product, what's going to happen? If you just look at the molecule, you note that to go from here to here, what has to happen? Something has to break, right? A bond has to break, okay? That bond ends up being this little thing here, where this carbon is bound to this nitrogen, okay? When we break bonds, do we have to put in energy, or does that release energy? Yeah, bond breaking, always you have to put in energy, okay? And so this, what we call the activation energy for this reaction, is going to be the difference in energy between the reactants and this point up here, which is what we call the transition state of the reaction or the activated complex of the reaction, okay? So this is called transition state. I'll put this here. Transition state, or the book also calls it the activated complex. And we frequently will denote this with this little weird symbol, right, where it's like a line and two little lines, okay? All right, so the activation energy for this specific reaction is going to be the energy that we have to input to break this bond. The minute that we break this bond, it flips up, we're at the transition state, and now it can immediately fall to the products because, again, these are at a lower energy state than the overall reactants, okay? So this is what I mean by activation energy, the energy that you have to put in to get a reaction to go in the first place, right? Even though it's exothermic, it's going to release energy, you still have to put something in to make it go. And that's what the activation energy represents, okay? Okay, what have I forgotten? I don't know. I don't think anything yet, but we'll see, okay? So we get to the transition state. Once it gets to the transition state, this is the highest energy state in the complex. It immediately falls to products, and that's a beautiful little isomerization reaction, okay? Okay, so what does the activation energy have to do with anything with respect to the rate constant or more specifically with the exponential factor, okay? So, again, just as a reminder, we have K is equal to A, the frequency factor, times this e to the minus EA over RT. And right now, we're talking about what this little bit implies with respect to the overall rate of a reaction, okay? Okay, so what this is trying to tell you, what the exponential factor is trying to say, is that this is the number of molecules, or the fraction of molecules that have sufficient energy to overcome the activation energy or the transition state barrier, okay? So what does that mean? So just as a reminder, we have these molecules, right? And our big assumption has been that they're floating around, and to react, they have to collide, right? But now what we're saying is not only do they have to collide, but they have to collide with sufficient energy, right? They have to be sufficiently energetic so that they do have enough energy to overcome that activation energy and fall to products, okay? What is that going to depend on? That they have enough energy. Where do they get their energy in the first place? Do molecules just hang around, do they just like suspend in air? They don't actually move? They're moving, right? Why are they moving? Right? So gases, they're moving. When we raise the temperature of gases, what happens to the kinetic energy of the gases? They go up, right? So kinetic energy is directly proportional to temperature, right? So as you raise the temperature of a gas, you're going to give it more kinetic energy. Why? Why does it have more kinetic energy? What does kinetic energy, how do we calculate kinetic energy? Mass times what? Velocity, right? Velocity squared, okay? As we raise the temperature, these guys start moving a lot faster, right? As they start moving a lot faster, they're going to hit each other with more energy, okay? This is where the temperature part comes in with respect to this exponential factor. If we raise the temperature, so if we make T really big, what's going to happen overall to this term? So let's imagine that this guy, activation energy, is small, and we make T really, really, really big. What happens overall to this thing up here? It's really small, right? So if this gets really small, what does it tend to? What number long term? 0. What does E raised to the 0? 1. Okay? What this is saying is that if you have a really tiny activation energy and a really high temperature, the fraction of molecules that have enough energy to overcome that barrier is equal to 1. Meaning every time they attempt it, they're going to overcome it because they have lots and lots and lots of energy. Okay? Okay, so what is the other side of this? Let's say when we have this guy that's really big, so a very large activation energy and a very tiny temperature. So this guy is really small. What's going to happen again to this term overall? We have big number divided by a small number. Who is it going to tend to? Infinity, right? So what does E raised to the negative infinity? 0, okay? The big manifestation of that, if the activation energy is really large and the temperature is really small, no molecules have sufficient energy to overcome the activation energy barrier, so nobody gets over that little hill, okay? Hill, okay. That's my Oklahoman accent coming out. Okay, so that's the frequency factor, or that's the exponential factor, right? It's telling you what fraction of molecules actually have sufficient energy to overcome this activation barrier, okay? What about the other thing, the frequency factor, A? So what we model the frequency factor as is essentially the number of times they try to overcome the reactivation barrier, right? So if we say we have some molecules and they're floating around, how do we kind of model their attempt at even trying to react? What was, again, a big assumption with respect to reactions? They have to do what? They have to collide, okay? So at first, we could think, okay, the frequency factor, again, if we're modeling it as the number of times they attempt to overcome the barrier, is just going to be the number of times molecules collide per given unit time, right? And so we actually have a number for that. If you have molecules in the gas phase, we know that they collide about 10 to the 9th times per second, okay? What happens, though, with respect to this frequency factor, is that this A tends to be much smaller than the actual number of collisions, okay? So why do you think that is? So A is much smaller than the actual number of collisions that happen in a given unit of time. Do you think every collision is going to lead to a successful reaction, ignoring the energy part? Okay, we'll come back to this. So we'll go ahead. Are you from the tutoring center?
Yes.
Okay.
Yes, I am. So for those of you that aren't familiar, we have a science tutor center on campus. It's over by the NS building. I believe it's NS 107, over where the labs and stuff are. We're open Monday through Friday from 7:30 to 7 p.m. 7:30 a.m. to 7 p.m. We do everything, physics, chemistry, organic chemistry, bio, anything you need. So yeah, I do chemistry and biology and physics. We have a few other people. We have people on staff like throughout the entire day that can do any subject you need. And it's been shown that people that come in to get help for like up to 10 hours, or like a minimum of 10 hours, get on average a letter grade higher in their classes. So yeah, don't hesitate to come in and get help. It's totally free for students, and you can be there as long as you want. Ask as many questions as you want, and yeah.
Is that 10 hours a week?
No, like 10 hours. No, like 10 hours total. Yeah, 10 hours total. If you want to be there 10 hours a week, you can. We have people that do that.
10 hours a week.
Yes.
That's 2 letter grades, actually.
Yes. Yeah. But yeah. So, any questions?
Did you say the times?
Yeah, 7:30 a.m. or maybe 8 a.m. to 7 p.m. Monday through Friday. Yeah, there's also a math center for those of you that need math help. They're also open Monday through Friday and on Saturdays, 10 to 2. But yeah. Okay. Right. Continue learning.
Thank you. Or continue not learning. I don't know.
Also, hi Alex. Hi Alex.
Okay, so back to this frequency factor thing, okay? Again, if we were going to model the frequency factor as just the number of collisions that each individual gas molecule has per unit time, we would find that this A tends to be much, much, much smaller than what that actual number of collisions is, okay? So why do you think that could be? So we will find that molecules, when they collide, sometimes they actually have very specific requirements on what's going to lead to a successful collision, okay? And I'll try to illustrate that when we actually look at some individual molecules, okay? So what's going to happen with respect to this frequency factor is that it's going to depend on 2 separate things. There's one thing that we call the orientation factor, and again, this is going to be a fraction in between 0 and 1. And another thing that we call the collision frequency, okay? So the collision frequency is just the number of times they collide per unit time, okay? All right, so what does this orientation factor have to do with anything, okay? So now let's imagine that we have 2 reactants, okay? A and B. And A and B are going to react to form AB, right? So this is great molecule AB, okay? Now, is there any specific requirement for B when it collides with A that's not going to lead to a successful collision, right? Can B hit A up here? Is that okay? Will it get AB? Right? Yeah, for the most part. Can B hit A over here? Yeah, okay. What about B hitting A over here? Well, we'll still get AB. Yes, right? So because these guys have no specific requirement with respect to orientation, this would be a reaction that would have a P that's very close to 1. Okay, so pretty much all collisions are going to lead to a successful reaction. Okay, now what if we had something like this, where we have NaCl combining with NaCl to form NO2 and chlorine? Are we going to have any specific requirements with respect to the orientation of this collision? Maybe certain orientations aren't going to lead to a successful reaction. So let's look at it, right? Let's look at the various ways that you could collide these 2 molecules and see what would happen, okay? So for this reaction, we have an NO, so an NO that's bound to a Cl, and an NO that's bound to a Cl. What do we make at the end? We make a nice NO molecule, so this part kind of stays together. What has to kind of hit? the CLs, right? The CLs kind of have to be near each other, and they have to collide with respect to one another so that we can break that O to Cl bond and actually form our ClCl, okay? So for example, if we had these molecules hit like this, do you think that's going to require, or do you think that's going to actually result in an effective collision? No, right? Because this would form like an NO or an NO, but it's not going to form a ClCl, right? What about this type of collision, where we have the chlorine hitting the N? Is that going to result in a successful collision? No, right? What about this type of reaction, where we have the chlorine directly hitting the chlorine? Do you think this is going to result in a successful collision? Yes, right? So this type of reaction, that's very complex, right? We make weird little molecules, has a very specific requirement with respect to the orientation of how they have to hit each other, okay? So because of this, P is going to be much, much, much less than 1, and it would be like 0.2 or 0.1, right? Because a lot of the times when they hit each other, they're not going to actually be in the correct orientation to get a successful collision. Only 1 out of every 10 times maybe they'll hit each other, which will result in a successful collision, a proper orientation, okay? Okay, lots of things go in to essentially increasing the reaction rate, right? So it's affected on orientation of reactants. It's affected on how many times they hit each other. It's also affected on who has enough energy to get over the barrier and go down to form products, okay? Okay, so then at the end of the day, we're always like, well, okay, that's great, it's a little theory and everything, but how do we measure these various things, right? How do we measure the activation energy of a reaction as well as this frequency factor, okay? So the way we're going to do this is it's going to come back to the Arrhenius equation, okay? If you watch the integrated rate laws, when we had these like rate laws, what do we have to do? We had to do specific things to them, right? It's kind of like the theme for the overall chapter. We always have to manipulate things to kind of get it in a form that is usable, okay? We're going to do a very similar thing here. We're going to manipulate the Arrhenius equation, and what we're going to do is we're going to take the ln of both sides, okay? So take the ln of both sides. We're going to be left with ln of k is equal to ln of a plus ln of e raised to the minus ea over rt. What is ln of e raised to anything? The value that it's raised to, right? Natural log correlates with the natural number. I don't know if that has a real name, but ln of this ends up just being this part, okay? So this guy comes down, and we're left with something that looks like this, okay? We can rewrite this in a different format by moving this part to the front and taking out the 1 over t, okay? And hopefully you'll see that this is beginning to take on the form of a line equation, okay? Well, what does that mean? How would we get anything from that, okay? So there are two things that we can actually measure that are in this specific equation. We can measure temperature, right? So we can control that. That can be our independent variable, and we can measure the rate constant, okay, at given temperatures, right? So some things that we can measure here are temperature and K, okay? So dot, 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 we can go in, change the temperature, measure the rate constant. That's great, okay? What we can also do with that is we can transform it, right? We can take 1 over t, right, where we just have our temperatures and we just take the inverse of them, and we also take the ln of k. We have the rate constants, we can just take the natural logarithm of it, okay? If we plotted that on some sort of nice pretty graph paper, where we put ln of k as the y-axis and 1 over t as the x-axis, we would get this beautiful little line, right? The slope for the line would be equal to minus ea over r, okay? And the y-intercept of the line would be equal to ln of a, okay? So we've got multiple different data points, we transform them, we plot them, and we tell our graphing program, hey, give me an equation for this line, okay? It does it, and it says, oh, the slope is like minus 0.63, and the y-intercept is like minus 0.62, okay? If we were given those data points, can we figure out what the activation energy is? If you have a number for slope, and we know what slope is equal to, right? It's equal to activation energy over r. Can you figure out what the activation energy is? Do you know what r is? Yes. If you have a numerical value for slope, So this is e to the a over r. Can you solve for e to the a? Yes, multiply r on both sides. That's how you get activation energy. What about a, the frequency factor? If we have a y-intercept value equal to minus 6.2, can you solve for a? We know that the y-intercept is equal to ln of a, so can you isolate a by itself? Yes, okay. So this is one way to do this. This is called an Arrhenius plot. For this, you need multiple values of k as a function of temperature, okay? So this would take, like, let's say, 4 data points to actually make one of these. You would plot it, and you would get the activation energy and the frequency factor from the data that you plot, okay? Unfortunately, getting 4 data points, so measuring 4 rate constant as a function of temperature, is very tedious and time-consuming. Instead, frequently you're left with is maybe only 2 data points, okay? So 2 data points would be a rate constant at a temperature and another rate constant at another temperature. We can still get data from just 2 data points, okay? What we use is something called the Arrhenius equation, the 2-point form, okay? Again, it's another derivation of the Arrhenius equation, which I'm not going to run you through. Unfortunately, if we only have 2 data points, what can we not get? So we're going to have a T1 and a K1, oops, not a Ki, a T2 and a K2. So what can we solve for here? If we know the K's, we know the T's, we know the R, we can get the activation energy, but what can't we determine from the 2-point form of the equation? A, the frequency factor, okay? So if you want the frequency factor, you've got to get multiple data points. If you don't, and you just want the activation energy, all you need to do is have 2 rate constants at 2 separate temperatures, okay? Okay, so how are we going to use this? Let's actually apply it in an example. So let's say we have this reaction where we have NO2 combining with CO going to form whatever. We don't care what the products are with respect to the kinetics, okay? We have a rate constant of 2.57 at a temperature of 701 Kelvin, and we have another rate constant 567 at a temperature of 895 Kelvin. We want to find the activation energy for this reaction. So what are we going to use? We have 2 temperatures and 2 rate constants. The 2-point form of the Arrhenius equation, okay? So I'm going to go ahead, because I like to keep track of everything. I have my T1 is equal to 701 Kelvin, and that correlates to a rate constant equal to 2.57 molar inverse second inverse. And then I have T2 equal to 895 Kelvin. Again, this is a rate constant of 567 inverse molar inverse seconds. Really quickly, what is the overall order of this reaction? How could you tell? What are the units of the rate constant? Inverse molar, inverse second. What does that correlate to with an overall order of the reaction? This would be second order overall. Okay, so just keep that flowing, keep that in your mind. Okay, so back to what we're actually trying to figure out. The activation energy, okay? So 2-point form of the Arrhenius equation looks like this. So K2 over K1 is equal to e to the a over r times 1 over T1 minus 1 over T2, okay? So we can go ahead and plug all of these various things in. This is what I need, my pre-done stuff. So we've got this guy, ln of 567 divided by 2.57 is equal to e to the a. What value do we use for r? 8.314. And what are the units there? Just as a note. Joules per mole Kelvin. This is going to be times 1 over T1. T1 is 701 minus 1 over T2, which is 895 Kelvin and Kelvin. Okay? So we multiply everything out, take the ratio of this, take the ln, and we solve for an activation energy equal to 145,185. What are my units? It's an energy, right? But where does the energy come from? Joules, right? Because we use this value of the R, this 8.314, this is in joules per mole. Do I like to leave it like that? It's a big number, significant figures, stuff like that. What's a better number to put this in? Kilojoules, right? So if I convert to kilojoules, this ends up being 145 kilojoules per mole. Easy stuff. So easy stuff. Activation energies. Okay, so we'll go ahead and try one on our own. So similar thing. We've got, this is ugly. I don't know if this is like an issue with PowerPoint or what, okay? So we've got two different rate constants at two different temperatures. First thing I want you to do is determine the activation energy for the reaction. And then I want you to apply that and tell me what the value of the rate constant is at 17 degrees Celsius. It's a little bit different than what I showed you in the previous example. Sorry. Okay, so that's what we talked about last time. The dependence on both temperature as well as activation energy, as well as, again, the orientation requirements when we actually have these collisions, okay? All right, so today we're going to talk about something a little bit different but kind of related, okay? We're going to talk about something called reaction mechanisms, all right? So let's consider this reaction, right, where we have H2 as a gas, and it has to collide with two ICLs, and in the process it's going to go to form two HCl's and an I2, okay? How many reactant molecules do we have right here? How many molecules do we have of reactants? 3, right? 3 molecules. We have one H2 and you have two ICLs, okay? How probable do you think it is that these guys are going to find each other, all 3 of them together, they're going to collide at the exact same time with the absolute correct orientation to lead to a reaction? How probable? 3 things finding itself in space. Not very probable, right? So not probable at all. So the probability of 3 things hitting each other with the correct orientation is essentially 0, okay? So how does this reaction proceed? Because it does, we see it. We see multiple reactions like this, where we have multiple reactants going to make multiple products. So instead of considering it all just happening once, right, with one collision, what we usually do is we propose what is called a mechanism, okay? And so a mechanism is kind of like a roadmap, where we essentially propose that this reaction, instead of happening in one step, happens in a series of steps, okay? Okay, so these series of steps are what we're going to call something called elementary steps, okay? And what they're trying to tell you is what's actually happening at the molecular level. What is colliding with what, and then what has to collide afterwards, okay? Okay, so for example, for this reaction, let's say we proposed the following mechanism, okay? So this consists of 2 separate steps. We have step number 1, which again, we're detailing what's actually happening at the molecular level. So in the first step, you have an H2 combining with an ICl. Okay, so what's the probability of those 2 finding each other? Pretty high, because it's only 2 things, right? They're going to go and make an HCl and an HI. Okay, and then in our second step, that HI that we just found, or we just made, is going to go and collide with an ICl to form another HCl and an I2. Okay, so that is our overall reaction, but we're saying it takes place in 2 separate steps, and those 2 separate steps only need 2 things to collide. Okay, so again, we're going back to probability. The probability of this guy happening is actually pretty high. So what we've proposed here, these 2 separate steps, again, are called elementary steps, and we call them that because, again, we're trying to show what is happening at the molecular level. H2 is finding an ICl, they're colliding, they're leading to the products, okay? HI is finding an ICl, they're colliding and leading to products, right? Okay, so note that with respect to these reaction mechanisms, we produce something that we've never really seen in this reaction before, right? So in this first step, we produce this HI guy. Does that show up ever in our overall reaction? No. So this thing is proposed, right? We make it, and then what immediately happens to it in the second step? We immediately use it, right? So we make it in our first step. We immediately use it in our second step, okay? And so when we sum our two steps, what happens to it? It cancels, right? So when we sum our two steps, anything that shows up as a reactant and a product in the same exact state will cancel. What do we end up with when we sum our two elementary steps for this mechanism? The overall reaction, okay? So that's one big thing with respect to these mechanisms, is that they always have to sum to the overall reaction that you were proposing a mechanism for, okay? So this thing that we made and then we immediately used is something called a reaction intermediate. It is a proposed species, right? Could we possibly know if this exists or not? So it depends, right? When we actually look at this reaction, all we know is that we put this guy in, we put this guy in, and what we get out is this and this, right? So for the most part, intermediates are proposed species, right? We can't actually isolate them because, again, these reactions are fairly quick, right? So the minute that this guy is made, it is fairly quickly used up in the second step, so usually you can't actually isolate one of these intermediates, but again, they're proposed to exist. Okay, all right, so we have reaction intermediates, right? We have these two elementary steps, and they have to sum to the overall reaction to give us a valid mechanism, okay? Okay, so a couple things that are really nice about these elementary steps that we will propose when we're proposing a reaction mechanism. Number one, each step has its own rate law, okay? So if it has its own rate law, that means it has its own little activation energy and its own little K. So each elementary step, again, has its own rate constant, its own activation energy, okay? Number two, the rate law for the overall reaction, how do we determine that? Right? How do we go in and determine a rate law for anything? We have to do it experimentally, right? So just like we're doing in the lab on Tuesday, we're going in, we're changing concentrations of our initial reactants, we're measuring the rates, we're getting the order from that, okay? So for an overall reaction, you have to determine the rate law experimentally, okay? What's great, though, about these rate laws for elementary steps is that they can be deduced just by looking at the chemical equation for the elementary step, okay? So what do I mean by that? If we go back to our little mechanism here, we had step 1 and we had step 2, right? In step 1, we have one molecule of H2 colliding with one molecule of HCl. We can look at that and say from that this is going to be first order with respect to H2, first order with respect to ICl, okay? We can essentially know the rate law for these elementary steps by just looking at how many reactants we actually have. Okay, so if it's a 1 in front, that means it is first order with respect to both of them. Okay, same thing for our second little elementary step. It is going to be first order with respect to HI, first order with respect to ICl. Okay, we can propose that just by looking at the elementary step. Okay, so what these rate laws are going to tell us is something called the molecularity of the reactions. This is a little vocabulary word that you should know, okay? What we mean by molecularity is we are saying in each elementary step how many things have to collide, okay? If you only need one thing to collide, we call this a unimolecular reaction. So you only need one thing. It's out there, it's on its own, we're waiting for it to react. This is going to be unimolecular. Okay? Again, for the rate law for this, because we can propose it directly from the elementary step, this is going to be just a first order overall rate law. Okay, so then another type of reaction is something called a bimolecular reaction. So a bimolecular reaction means that we have two things that are colliding in the elementary step, okay? So this can be either two of the same things, right? So this could be an A colliding with another A, right? So this would be 2A going to make products. We still have to have two things colliding, or this could be an A colliding with something else going to make products, okay? There are two separate rate laws for this. The rate law for this guy, since this relies on two A's finding each other, is a second order, okay? So if there's a 2 in front of an elementary step, it's going to be second order with respect to that reaction. On the other hand, if we have just 1 and 1, then it's going to be first order with respect to both of the reactants, okay? Overall, though, for both of these bimolecular reactions, what is the overall order of the reaction? So it's either second order with respect to one reactant or first and first, but what is that overall going to be? Second order, right? So for bimolecular, overall, these are both going to be second order reactions, okay? All right, so then the third one is something called termolecular. Okay, so termolecular means you have three separate things colliding at the same time. How probable do you think this is? Again, when I introduced the whole H and 2, I said that's really improbable, right? It's not going to really happen. So for these guys, termolecular things, three things colliding at the same time, these are fairly rare. So you don't really need to know about them at all for the most part, okay? But you do need to know the vocabulary of a unimolecular reaction as well as the bimolecular reactions, okay? One thing or two things colliding. Okay, so vocab, molecularity, moving on to the most important part, okay? So again, these mechanisms are proposed roadmaps for what is happening in our chemical reaction, okay? A scientist will go in, they'll propose a mechanism, and then they will try to verify that mechanism. So how do they do that, okay? So each mechanism is always going to have something called the rate determining step. We will frequently abbreviate this as RDS or a rate limiting step, RLS. A rate determining step is essentially going to be the slowest step in the mechanism. So it's the step that goes the slowest, essentially limits the entire rate of the reaction because of that, okay? A nice little analogy to this is traffic, okay? So let's say that when you go home, you're going to go home, and we can imagine that your route home is going to occur in three separate steps, okay? So the first step we'll call step number 1, the second step we'll call step number 2, and the third step we'll call step number 3, okay? So now imagine that in step number 1, you're just driving down the 101 very, very, very fast. So let's imagine going 80 miles per hour, okay? In step number 2, though, the road narrows, right? And so instead of 3 lanes or however many lanes, let's imagine that it narrows down to just 1 lane. So 1 lane of traffic, okay? Step number 2. How quickly do you think you're going to get through that 1 lane? Not very quickly. So let's just imagine, let's just propose some sort of speed like 2 miles per hour, okay? All right, so then in step number 3, it clears up and opens back up again, and everyone starts flowing again at a nice 80 miles per hour. When we want to know how quickly you get from A all the way to C, which one's going to determine that? 2, right? And essentially, what do you think long-term your rate in going from A to C is actually going to be? Similar to, right? So imagine, takes you 5 minutes, takes you an hour, takes you 5 minutes. When you go from A to C, whose rate really determines your overall rate through that way? The second one, right? So overall, your rate in going from A to C is very, very, very similar to the rate of the rate determining step, or our second step in our reaction here, okay? It's exactly the same thing with respect to a chemical reaction, okay? A rate determining step is going to slow the reaction down so much that when you measure the rate of the reaction, all you're really measuring is the rate of the rate determining step. Now the big part of this is that when we're watching the rate of the overall chemical reaction and we're measuring the rate law for that rate, what we're really measuring is the rate law of the rate determining step, because it's essentially bottlenecking everything and all we're really watching is that step, okay? Now, what's the big thing here is if we have an elementary step, can we predict the rate law just by looking at our proposed elementary step? Elementary step, can you look at the number of reactants and propose the rate law for it? Yes, right? Okay? So because of that, to be a valid mechanism, the rate law of the rate determining step has to be the same as the one that you determine experimentally. Okay? So there are two big keys, two big takeaways from this. To be a valid mechanism, you have to, number one, sum to the overall reaction, okay? And number two, the rate law that you determine experimentally has to be the exact same as the rate law for the rate determining step, which you can essentially know by just looking at what you've proposed in the mechanism, okay? So for an example of that, let's go back to this thing that we actually did measure the rate law for, okay? NO2 combining with CO going to form whatever. We don't really care about products with respect to reaction mechanisms, okay? At some earlier date, we measured that the rate law for this reaction was second order with respect to NO2 and zero order with respect to CO, okay? Now, we have proposed a mechanism, okay? And in our mechanism, we have a first step where we have to have two NO2s collide, okay? And in the second step, we have something that we made in the first step, this NO3, it has to collide with the CO, goes to make products. To validate this mechanism, the first thing that has to be met is that this combined has to sum to the overall reaction, right? So when we add these two steps together, do we get our overall reaction? So we have an NO3 that is produced here that is immediately used in the second step. What is this called? Something that is made in an early step and then used in a subsequent step. We call that a what? It's an intermediate, right? So NO3 here is an intermediate. So that's going to cancel. What are we left with? We have an NO2, but we have two NO2s here. So what am I going to be left with respect to that? I have one as a product, two as reactants. So this guy's going to go away. This guy's going to go away. We're going to be left with one. Can I cancel anything else? No. So we're left with this guy plus this guy and a CO2 plus an NO. Does that sum to our overall reaction that we're looking at? Yes. Okay. So that's number one. Step number one in validating a mechanism, check. Number two, the rate law of the rate determining step has to match the rate law for the overall balanced chemical equation that you have determined experimentally. This is what we determined experimentally, right? This is the rate determining slow step. In looking at it, we know that this is a bimolecular reaction, right? We have an NO2 and an NO2 and they have to collide. So what order is that with respect to NO2? If we're just proposing the rate law by looking at this elementary step. Second order, right? It's second order with respect to NO2. So we can propose that by just looking at it. Does this match this? Yes, okay? So because of that, this is a valid mechanism. What we have proposed here could potentially be what is actually happening in the chemical reaction, where we have overall this going to make this, okay? One thing to note, again, like I said earlier, each of these elementary steps has their own rate law associated with them. They have their own rate constants, and they have their own activation energies, okay? So when we look at these reaction coordinate diagrams, like we showed you before, where we have reactants going to products, this is essentially going to manifest itself as two separate humps on the curve, right? The one with the largest activation energy is going to be the one for the rate determining step, okay? Our little intermediate species are going to be little things that kind of lie in here, and again, they're going to go to our next step, and they're going to collide and make the products. Okay. That's big. I want you to realize that. You probably don't get that, and I understand. It doesn't make any sense. It never did to me either, but long term, this is how we know anything about chemical reactions, okay? Okay, so just like I said, if we have a mechanism and we want to validate it, it has to meet two requirements. It has to sum overall to the balanced chemical equation that we were proposing it for, and also the rate law of the rate determining step has to match the rate law that we have determined experimentally for the overall chemical reaction, okay? It's important to note here that a mechanism can only be validated, right? It can be said, okay, yeah, this makes sense and it matches our experimental data. It can never actually be proven because there are an infinite number of ways a reaction can actually occur, and you could never actually go through and test every single one, okay? A good little handle on helping to validate and prove your mechanism would also be to be able to isolate one of those intermediate species. If you're proposing something that is made and then immediately consumed, but you can isolate it, then that is a really big, helpful step in actually validating your mechanism. Okay, so how would you actually see this appear in a question on an exam or a question in the homework, okay? So let's say I gave you something like this, where I have a proposed mechanism and I ask a bunch of questions for it, okay? So in this mechanism, we have two separate steps, and both of these steps are bimolecular, okay? The first step is our slow step, and the second step is our fast step. The first question asks, what is the overall net chemical equation that this mechanism is being proposed for? How could I determine that? So what is the first big thing with respect to mechanism? What do they have to sum to? The overall net chemical equation, right? So if they're asking me, what is the overall net chemical equation that is being represented by these two steps, what would I need to do to figure that out? Just need to add them together, right? Cancel the intermediate species, and that's going to give me my net overall equation. So when I do that, I have this guy, okay, it doesn't get canceled by any guy. I've got this guy, which is made and then immediately consumed. So that's going to get canceled. And what am I left with? So for one, my overall reaction is going to be S28, 2 minus, plus how many I minuses? 2. 2 I minuses going to make 2 SO4, 2 minus, plus an I2. So this is question 1. All right, question 2, identify any intermediates. Are there any intermediate species in this mechanism? Have we made something and then immediately used it? What have we made? I plus, right? So if it asks you to identify an intermediate, all you would have to say is there's one, and it's I plus. Okay, so then number 3, what is the molecularity of each step? How would I determine that? It's just a vocab word. What am I looking for? How many things collide, or how many reactants do I have in each elementary step? Okay, so for the first step, is this a unimolecular, a bimolecular, or a termolecular reaction? It's bimolecular, right? Because I have one thing colliding with another, first order with respect to both. So this is bimolecular. What about the second step? It's also bimolecular, right? I have an intermediate colliding with one of our reactants to form our product. So both of these guys are bimolecular. So this is the answer here. And then last, what is the rate law for the overall reaction? So this is valid. They've already told us this is a valid mechanism, right? What does the rate law for the overall reaction have to be the same as? The rate law for the rate limiting slowest step. okay? The slowest step is the first step. Can I propose a rate law for this step just by looking at it? Yes, right? So what is it? Rate is equal to K, and then what? S208 to minus first order, and then what else? I minus also first order. If this was a 2 in front, what would my rate law have been? Second order with respect to S208, first order with respect to I minus. When we're looking at what these orders all are, all you're looking at is the coefficient in front of each reactant, okay? If it's a 1, it's first order. If it is a 2, it's second order. If it's a 0, if it doesn't even exist, it's 0 order with respect to that, okay? Okay, so that's all I'm going to say about that. There's only one thing or two things that I want to kind of talk about here at the end. So last class we talked about mechanisms, right? Reaction mechanisms. And the purpose of mechanisms is that for the majority of reactions, these reactions are going to occur in more than one step, right? And so the mechanisms that we propose for a chemical reaction is essentially that like roadmap or that series of various steps that the reaction is actually trying to go through, okay? So when we propose steps, we call those elementary steps. And so what's really great about elementary steps? So for an elementary step, can we propose the rate law just given the stoichiometry of the reaction of the elementary step? Yes, right? So that's what's so great about elementary steps is that the rate law can come directly from the chemical reaction for that step. We can't do that for overall reactions, right? We have to experimentally determine the rate law, okay? So when we propose a mechanism, we have to validate it. And to validate a mechanism, it has to meet two criteria. Okay, so first off, all of the steps, all of the elementary steps that you have proposed have to sum to the overall chemical reaction. Okay? And number two, the rate law of the experimentally determined rate law has to be the exact same as the rate law for the rate determining step, elementary step. Okay? So in this last little slide, we went through kind of an example problem that you could see on a exam, right? And in that problem, which I don't want to go back to because I think it messes up the recording, the first step was the rate determining step, right? And so you could look at it, you could say, hey, this is the rate law, it matches the experimentally determined rate law, so we have a valid mechanism, okay? So now what I'm going to show you right now, I'm not going to go deep into this because I'm not going to explain it all that much, but what happens if our rate determining step is not the first step? Right? So let's say we have an equation here, so a chemical reaction, okay? We have our experimentally determined rate law, okay? And we have a proposed mechanism. And in this mechanism, which is the slow step? Is it 1, is it 2, or is it 3? It's 2, right? So you may say, well, what's the problem with that? So let's go ahead and look at our slow rate determining step and propose a rate law for this step, right? So if this guy, if reaction number 2 is our rate determining step, then the rate law for this is going to be K times the concentration of H2, first order, because there's a 1 in front of the H2, times concentration of N2O to, again, first order, because there's a 1 in front of it, okay? So now looking at this proposed rate law compared to our overall chemical reaction, what's the problem with being able to validate this? Right, so remember we have to experimentally determine these rate laws. What is N2O2 in this overall reaction? Is it a reactant? No, it's an intermediate, right? So what's the problem with that? How could we experimentally show that, this rate law, the overall rate law, depends on something that we can't actually even isolate or, measure, okay? So this is the issue. I'm going to leave this here, though, because this goes into equilibrium, which is the next chapter, right? So we can essentially define this guy in terms of things that we can measure as long as we make a bunch of assumptions. I'm not going to talk about that yet. We'll come back to this at the end of chapter equilibrium, whatever number it is, okay? So for right now, all you guys can do is validate a mechanism that has the first step as the rate determining step, not a subsequent step, okay? And again, we will come back to this, I promise, once we get into equilibrium. Okay, so after that, what else do we have to talk about? One last thing. That is catalysts, okay? All right, so with respect to rates, right, we now know two different factors that affect the overall reaction rate of a reaction, okay? One is concentration and one is temperature, okay? So let's say that we have a reaction and we want to speed it up, right? We want it to go a lot faster than what it's actually going. There are two different ways we can do that, right? We can increase the temperature, we can increase the concentration of our reactants. There is a limit to that, though, right? So there's only so much stuff that we can put into a reaction vessel, and there's only so much of a temperature that we can increase the temperature to until we're going to start getting unwanted side products or just complete decomposition of our starting material, okay? So there's one other way that we can speed up a reaction, and that is by using something called a catalyst, okay? So a catalyst is a thing that increases the rate of a chemical reaction. In doing so, it is not actually consumed in the overall reaction. Okay, so catalysts are never consumed, but they do increase the rate of a chemical reaction. All right, so how do catalysts actually go about doing this? How do they increase the rate of these chemical reactions? Okay, so what catalysts do comparatively to just normal kinetics is that they offer an alternative pathway. Okay? They offer an alternative mechanism whereby they decrease the activation energy of all of the various steps. Okay? So again, if we decrease the activation energy, what is that going to do to the overall rate of the reaction? It's going to increase it. Okay? So that's what catalysts do. They offer an alternative mechanism whereby they decrease the activation energy of all of the various steps. Okay? So for example, the ozone layer is out there in the ozone layer, okay, it naturally decomposes on its own, okay, so out there decomposes naturally by itself without any extra help, okay, but the problem with that is that reaction, that natural decomposition of the ozone layer is incredibly slow, it's incredibly kinetically inert, so for the most part, the ozone layer just stays there, okay, it stays there until we introduce things like chlorofluorocarbons. Okay, so they introduce chlorine into the ozone layer, which acts as a catalyst in this decomposition reaction. Okay, so it catalyzes the decomposition of ozone into O2, which is not good because the ozone layer protects us from the harmful UV rays of the sun. Okay, so note that this is the alternate mechanism by which these chlorine molecules act as catalysts. Okay, so note that we have one step and we have two steps. Okay. So again, for this to be a valid mechanism, what do these guys have to sum to? The overall balance reaction, right? So if we summed everything up, we would find that this sums to our overall balance reaction, okay? But now note, do we have an intermediate in this reaction? So do we make something in an early step, but then we utilize it in a subsequent step? Yes, right? So we make ClO in this first step. It is immediately consumed in the second step, right? So this is a reaction intermediate. Now compare that to what chlorine does. Chlorine, again, is acting as a catalyst in this reaction. So in the first step, what do we do with chlorine? We use it, right? But then what happens to it at the end? It comes back, right? So it's remade in a later step. Okay, so again, catalysts do this. They speed up these chemical reactions, but they are not consumed in the overall reaction. That is a hallmark of a catalyst, okay? So usually how they manifest themselves in these mechanisms is that they are used in an early step, but then remade in one of these later steps, okay? So how would you identify the difference between an intermediate and a catalyst? Intermediates are made and then consumed, whereas catalysts are used and then remade. So they essentially overall are not consumed in the reaction. Okay, so this guy is our catalyst. Okay, so again, how do they do this? How do they speed up the reaction rates? So this reaction, by itself, without the help of any type of catalyst, occurs in one single step, and it is extremely slow. So what can we assume about the activation energy for this single step, slow, terrible reaction? It's very high, okay? Now catalyst, our little catalyst chlorine here, again, it alters an alternate pathway. And what it's going to do is it's going to decrease the activation energy for this overall reaction so that this guy goes a lot faster. Okay, so the blue line here is this decomposition of ozone in the uncatalyzed reaction. So we have a very large activation energy, right? And then the red is our catalyzed reaction. So even though it occurs in two steps, the activation energy for both of those steps is very, very, very small comparatively. And so overall, we get a much faster reaction, okay? So if I were to give you something like this reaction coordinate diagram, you should know which one would be the catalyzed reaction and which one would be the uncatalyzed reaction just by looking at the magnitudes of the activation energies, okay? Okay, so good, catalyst, great. It's made, or it's used, and it's remade, so it's not consumed in the overall reaction. So what is the most important catalyst that you guys know about, that you should know about? So enzymes, right? So we utilize enzymes every day in our body for every chemical reaction. Even that poor little lizard was using enzymes to catalyze his chemical reactions that allowed him to move, okay? So what are enzymes? Enzymes are the biological catalysts, right? They are consistent. Oh, darn it. Enzymes. Enzymes are biology's catalysts, right? So they are consistent of proteins. What are proteins made up of? Amino acids, right? Amino acids strung together to make these big, giant macromolecules, okay? So how do enzymes catalyze reactions? So inside of every little protein enzyme, there is a spot called an active site, okay? The active site is where the reactant of the chemical reaction binds. So in biology, we call this reactant, we call it a substrate. For whatever reason, I don't know why they change words with respect to various disciplines, but in biology, the reactant in a chemical reaction is called a substrate. It binds to the active site of the enzyme. So how do you think enzymes catalyze reactions? What are they going to do long term versus an uncatalyzed, non-enzymatic reaction? They're going to alter an alternate pathway that lowers the activation energy. Specifically, what enzymes do is they essentially bind the highest energy part of the reaction, right? They have these various little functional groups inside their little active site that help bind and stabilize the transition state, okay? So we went back to that energy profile diagram. The transition state was the one at the very highest bit, okay? So by binding that and stabilizing that, that allows it to lower the activation energy, which again increases the rate of the chemical reaction, okay? So what do enzymes do? They bind and stabilize the transition state, which lowers the activation energy required to get it to that transition state, okay? So then, that was the last slide. We'll go